So before I get started, I'll just remark that this interesting optical effect you see on the screen, I'm told it's caused by the fact that the heat was turned on and you're seeing hot air rising in front of the projector. If you wouldn't have expected it to produce this effect, that makes two of us. Okay. So I'll be trying to develop a version of the replica trick to calculate the entanglement entropy of the vacuum in string theory. So let's first remember the replica trick in field theory. So in quantum field theory, we want to calculate a density matrix rho for the vacuum state in a half space, where the half space, let's say, is non-negative x, where x is one of the spatial coordinates. And there's a well-known argument that you can do this by a path integral on a cut version of R2 times the remaining coordinates. So R2 parameterizes the time and also x, where we have localized the half space. And you compute the path integral on this cut space. And it produces a function of two sets of field variables. One is just below the cut, and one is just above the cut. And so it gives a path integral. The path integral gives a function, slight misprint here. The function depends on two sets of field variables, phi r and phi r prime, which are field variables just above or below the cut. And a function of a pair of variables in general can be viewed as a matrix acting on just one set of the variables. So this is the density matrix rho of Rindler space. This funny thing was probably meant to be rho. Now suppose, for example, you wanted to calculate the trace of rho squared. Well, if rho is a matrix whose matrix elements are rho of phi and phi prime, then the trace of rho squared would be like so. And since we compute the matrix element of rho with the path integral on a cut plane, well, two rows with the two cut planes. And as actually one of the speakers explained yesterday, we then glue the top, Meroff explained yesterday, we glue the top of the cut in one to the bottom of the cut in the other, and vice versa. And by just because we want to contract this index with this one and vice versa, and gluing one cut to the other, what we produce is a double cover of the plane with a branch point at the origin. So, well, more exactly, since d minus 2 dimensions have been spectators, we've built a double cover of the plane times Euclidean space of dimension d minus 2. And similarly, if we wanted to compute the trace of rho to the n for any integer n, any positive integer, we'd define an n-fold cover of the plane branched over the origin, say R2 sub n, and do a path integral there. Now suppose we want to compute the entanglement entropy of Rindler space, which formally is minus the trace of rho log rho. Well, if we could calculate the trace of rho to the n for every n, then this would be easy, because if f of n is the trace of rho to the n, then the entropy is minus f prime of 1. Now, in the particular example I've been describing of quantum fields in a background spacetime, we can, in fact, directly compute this function for every positive n, not necessarily an integer. The reason is that the n-fold cover of the plane can be viewed as a cone with a cone angle of 2 pi n. And a cone makes sense for any angle. So, for example, if you want a cone with an angle of roughly 2 pi over 8, which is what I've drawn, this is an angle of roughly 1/8 of 2 pi. Well, we just make that angle in the plane, and then we glue the top to the bottom and make a cone of that angle. And a path integral on a space with that cone angle, formally at least, would give us a way to compute trace of rho to approximately 1/8 with the way I drew the cone. But suppose we didn't have this way to access trace rho to the n for non-integer n. And the reason I'm supposing this is that we'll be in that situation in string theory. Then we could reason as follows. If rho is a density matrix, that is a positive matrix with trace rho equals 1, then trace of rho to the n is holomorphic and bounded by 1 in the half plane where real part of n is at least 1. Carlson's theorem says that a function holomorphic in that half plane with reasonable growth conditions is uniquely determined by its values at positive integers. So if we can calculate trace rho to the n for integer n, And then if we can find an analytic continuation to the whole half-plane with some bounds on its growth at infinity, then that'll automatically give us the right answer through the half-plane. And then we can differentiate it at n equals 1. Well, in string theory, we can't follow the usual replica procedure because there's no known conformal field theory, and moreover, there probably isn't one, whose target space is an n-fold cover of R2 branched over the origin. However, an alternative has been suggested in the form of an orbifold, R2 over Zn. So, well, the orbifold has a target space that's a cone of opening angle 2 pi over n. The orbifold is a conformal field theory whose target space is not an n-fold cover of the plane. Rather, it's a quotient of the plane by Zn. So if n were 4, you would take one quadrant in the plane, say this quadrant, which you could think of as the plane divided by Z4. Then you glue the two edges together, and you make a cone with an angle of 2 pi over n, where in that example n is 4. So formally, the orbifold conformal field theory tries to compute the trace of rho to the 1 over n. Well, you might hope to use the orbifold to compute the trace of rho to the 1 over n for integer n, and then analytically continue to other values, maybe using Carlson's theorem again. There's a problem with this. The orbifold is actually tachyonic in the closed string channel. So if you try to compute the trace of rho to the 1 over n in perturbation theory by summing string loops in the orbifold, you're going to run into exponential divergences. So you need to do something a little bit better. But you shouldn't panic because this might be the right answer. In quantum mechanics in general, the trace of rho to the 1 over n can be divergent when the real part of 1 over n is less than 1. But it does show that we need to be a little bit more sophisticated in what we do. We can't literally compute trace of rho to the 1 over n and then analytically continue it because, at least if the orbifold method is correct, for positive integer n bigger than 1, the trace of rho to the 1 over n is divergent. But there is an obvious thing you can do instead. So these string amplitudes are integrals over moduli. So for instance, the one-loop correction to trace rho to the 1 over n comes from a one-loop integral, which in the open string case comes from a worldsheet that's an annulus. And the formula would be this one, where Zn of t is the partition function of an annulus whose modular parameter is t. Now, for the orbifold, Zn of t is well defined, although the integral over t is divergent when n is an integer. So you can try to analytically continue Zn of t and then integrate over t later. Unfortunately, I don't know how to do the closed string version of this problem, which would be more interesting because the closed string sector contains gravity. But in the open string case, you can explicitly find the unique analytic continuation of Zn of t that satisfies the conditions of Carlson's theorem. So I wrote here I'll start with, but that was reflected an optimistic view of how far I'd get in these slides. I'll mostly tell you about the simplest open string problem, which is a DP brane that crosses the Rindler horizon in type 2 superstring theory. So its world volume is Rp plus 1, but we'll factorize it as R2 times Rp minus 1, where R2 are the particular two dimensions where we do the orbifolding. So R2 is going to be replaced by the cone. So we'll study a DP brane whose world volume is the cone times Rp minus 1.
Can I ask a question?
Yes?
So sometimes when we have orbifold, you secretly turn on some antisymmetric tensor field. Is this not happening here?
Which one do you want to turn on?
So well, it depends on the situation, but sometimes the NSNS2 form can be turned on.
You mean a twisted sector?
Yes.
So you have in mind discrete torsion?
Yes.
Well, with the Zn orbifold, you can't have discrete torsion. Zn times Zn would give room for that, but Zn doesn't.
Oh.
But since you ask, I'll remark the following. I won't really have time to explain it, but Dalbekar and I have done a more recent calculation in type 1. And in type 1, you have tadpoles, and the orbifold has twisted sector tadpoles. So you have to do something to cancel them.
Oh.
So that's at least in the spirit of your question.
Thank you.
But, well, one reason I'm talking about the DP brane today is that it fits better in 35 minutes, since we don't have to cancel any tadpoles. So as I said, we're going to take the world sheet partition function of the string on the annulus, and we'll find its unique continuation from integer n to a half plane. And there's actually one nice thing which happens, which is the nicest thing I have to tell you today. Well, actually, it takes two parts. The first part is that for Carlson's theorem, we want analytic continuation is unique in the half plane where the real part of n is at least 1. But it turns out that the unique continuation that's analytic in that half plane is analytic in a bigger half plane where the real part of n is at least 0. So as a bonus, we'll get more holomorphy than we were looking for. And the reason that's important is that once we have holomorphy when the real part of n is bigger than 0, we also have holomorphy when the real part of curly n is bigger than 0, where curly n is 1 over n. In particular, we'll get holomorphy when the real part of curly n is bigger than 1. And that's where we would like to be, because in quantum mechanics in general, the trace of rho to the curly n is well behaved when the real part of curly n is bigger than 1. So in the orbifold, we start in the wrong region, where curly n is 1 over an integer, so it's less than 1. And because of what I'm saying here, we get holomorphy in the, we can continue from curly n less than 1 to the region we want, where curly n is bigger than 1. Now, now I get to the second, well, better part of what happens. So as usual, you can extract some information about the closed string sector by studying the open string partition function for small t. So as I remarked, I don't know how to analytically continue the orbifold in the closed string sector, but you can learn something about the closed string sector from the open string sector. So it turns out that to the extent you can probe the closed string sector this way, it's tachyon-free when the real part of curly n is bigger than 1. So remember, I remarked that you can't calculate the trace of rho to the 1 over n for integer n, or you can, but it's infinite, because of the closed string tachyon of the orbifold. But when you continue, at least by the method we'll do today, to the real part of curly n bigger than 1, the closed string sector stops being tachyonic. So at least there's no exponential divergence in the integral that's supposed to compute trace of rho to the curly n for curly n bigger than 1. Now, the integral can still have a power law infrared divergence for small t because of massless closed string states. In fact, you should expect such a divergence if p is too large. That's because of well-known infrared problems with DP branes. So this would happen if you were computing scattering amplitudes rather than entropy. There are well-known infrared divergences with DP branes when p is too large. So in answering Hiroshi, I remarked that for D9 branes, one has to worry about tadpoles. So we expect it to bound on p, but the power law divergences are worse than expected by 1 or 2 powers of the proper time in the closed string channel. So p has to be smaller than I would have expected. And the physical interpretation of that isn't clear. So now I'm going to explain the strategy for analytic continuation. So here I've drawn an annulus, which is meant to have a thickness of pi, and the other direction, the circle direction, is supposed to have a length 2 pi t. I left out the t here, I guess. But that would be 2 pi t, where t is the modulus of the annulus. So let curly h be the open string Hilbert space in R10, and curly h sub n is the open string Hilbert space of the orbifold. For open strings, the Hilbert space of the orbifold is gotten from that in R10 just by projecting onto the Zn invariance. For closed strings, it's different, as you have to add twisted sectors. And the annulus partition function is just a trace in the annulus Hilbert space of e to the minus 2 pi times the Hamiltonian times the time, with an insertion of minus 1 to the f that distinguishes bosons and fermions. And you can write this as the trace in the full Hilbert space of R10 with insertion of a projection operator P. And the projection operator is just the projection operator onto Zn singlets. So it's 1 over n times the sum over all elements of Zn. So if I let Zkn of t be the trace with an insertion of u to the k, where u is a generator of Zn, then the worldsheet partition function of the orbifold is just the sum of these twisted partition functions. But the k equals 0 contribution actually vanishes because it's the untwisted sector. It vanishes because of the underlying supersymmetry. So I could just let the sum run from 1 to n minus 1. It's also fairly standard to define the variable tau, which is I times t. So when I write holomorphic functions in a moment, I'll do it in terms of tau. Now, on this page, I'm going to explain the facts that will make analytic continuation possible. So there's a meromorphic function j of z and tau with the following properties. First, the twisted partition function is a value of j of z and tau, where z is equal to k over n. Secondly, j of z and tau is periodic, and it's also an even function of z. Its residues vanish very rapidly at infinity, and its poles are only when the real part of z is 0 or a half. And they're almost all simple poles. We'll ignore today the fact that there's one double pole. So the existence of j is a restatement of standard facts, and I'll explain it in a moment. Given that there is such a j, the partition function on the annulus is a sum of values of j. And now I consider this nice function, which I call k. It's a periodic function. It's bounded, except if you keep away from its poles, which are on the real axis. And its poles in the strip between 0 and 1 are simple poles of residue 1 at z equals k over n, for k an integer. Now, both k and j are periodic under z going to z plus 1. So let's make that identification and therefore work on a cylinder. We can view the orbifold partition function as a sum of residues of the function kj at the poles of k. Because, well, first of all, j does not have poles at the poles of k. So the residue at a pole of k is just 1, the residue of k, times the value there of j. So this is just a way to write an expression for the sum of certain values of j, and the sum of those values of j is the orbifold partition function. But the sum of all residues of k times j vanishes. So I can write another formula for z sub n as minus the sum over all the other residues. And the other residues come from poles in j. So here's another formula. Now we're summing over poles of j instead of poles of k. So if the poles of j are all simple poles, I can pull k out from the residue expression, and we just get a sum of residues of j times values of k. There's actually one double pole, so there's a small modification which I won't explain. Now, what's nice about this formula is that the values of z, where we have to sum, do not depend on n, because they come from poles of j, and j doesn't know about n. So n only appears inside this function k of z and n, which was an explicit function. So all we have to do is analytically continue k of z and n. So by Carlson's theorem, if there's an analytic continuation of k of z and n, holomorphic in the half plane and obeying some bounds, then it's unique. Well, here we run into a slight surprise. For fixed z and suitable real part of z, the analytic continuation suggested by Carlson's theorem does exist. But it's not analytic in Z. It only exists for special values of the real part of Z. But we only need to continue k of z and n at the values of z where j has a pole, and those are when the real part is either 0 or half. So we only need to analytically continue k of z and n when the real part of z is either 0 or half. And we can do that with no trouble by explicit formulas I'll write in a second. For integer n, here's another formula for k of z and n. You can check that that's equivalent to the function I had written before. If the real part of z is 0, it's holomorphic in n when the real part of n is bigger than 1. It satisfies the appropriate bounds. So it's the unique continuation from positive integers with those properties. And there's a bonus. It's actually holomorphic in a bigger half-plane, where the real part of n is non-negative. This depends upon z having real part 0. So this is the analytic continuation of k of z and n, provided by the unique one allowed by Carlson's theorem when the real part of z is 0, and has a bonus larger holomorphy. If the real part of z is half, we have to be more careful and continue from odd positive integer values. That's natural because we actually will study an orbifold for odd n. An analogous orbifold for even n is slightly different. And since we're interested in n equals 1, it's more natural to continue from odd values of n. For n, an odd integer, an alternative formula for k is this one. It's not immediately obvious, but if you think about it a little while, you'll discover by checking residues, poles and residues, that this is another formula that when n is an integer is equivalent to the original formula for k. And this one, for real part of z equals half, is holomorphic in the half-plane. And it's even holomorphic in the larger half-plane. Now, so that's how we're going to continue k. Now let me explain why there's a holomorphic function j, whose values at certain points are the orbifold partition functions. The basic reason is that open string modes on the annulus are related, as usual, to chiral closed string modes on a genus 1 Riemann surface that's a double cover of the annulus branched over its boundary. So open string modes bouncing back and forth between the boundaries are the same as chiral closed string modes. You see, a massless particle bounces back and forth. It could just as well be on a circle, a massless mode that only travels to the right. In other words, a chiral closed string mode. So the annulus is closely related to the partition function of purely right-moving closed string modes on a genus 1 Riemann surface with the modular parameter tau. Moreover, the Zn orbifolding group is a subgroup of the U1 symmetry of R2. And using the U1 symmetry, you could twist the torus partition function by phases, 2 pi phi 1 and 2 pi phi 2, going around cycles in the torus. So what twisting by phases means that when a closed string mode goes around a circle, it comes back with a rotation by an element of U1. And we can independently do that around this direction or this direction. And as long as we only consider chiral modes on the torus, the twisted partition function is holomorphic in phi 1 plus tau phi 2, which I'll call z. And then we find that if z is k over n, the twisted partition function is z sub kn, the orbifold twisted partition function. So from this, you'd think that they're the doubly periodic function. Let g of z and tau be the twisted partition function of the chiral modes. From what I said, you might think that g of z and tau would be the same as the orbifold partition function. This should be z, not tau, is k over n. It's not quite true because the relation of open string and closed string modes doesn't work for zero modes. And because there's a factor that corrects the naive idea because of the zero modes. So the correct formula is this one. So g of z and tau is the partition function for a chiral set of closed string modes. This is a factor that comes from the zero modes, and z is just a constant, well, which also comes from zero modes. V is the volume of the intersection of the dp brane world volume with the Rindler horizon. And c and the 1 over sign come from zero modes, as stated here. So, as I said before, it's important that the orbifold partition function, analytically continued, only has poles when the real part of z is 0 or half. That's most obvious in the Green-Schwarz formalism. The partition function for the chiral zero modes is a ratio of fermion and boson determinants. And the only way it can have a pole is when the determinant of d sub b vanishes. The determinant is just a product of eigenvalues. It's never infinity, but it can be 0 when there's a zero mode. A fermion zero mode would give a 0, but a boson zero mode gives a pole. So poles come from zero modes of d sub b, and it's straightforward to find the values of z at which they occur and to get the answer that I said. I won't do it in front of you, but it's straightforward. One more thing we need to know is about the closed string partition interpretation of the annulus partition function. The annulus describes an open string of width pi, this way, propagating for Euclidean proper time 2 pi t this way. Equivalently, in the cross channel, we have a closed string, this one, with circumference 2 pi t, that propagates sideways for a proper time pi. If we rescale length so the closed string has standard circumference 2 pi, the proper time in the closed string channel is pi over t. In other words, if I make this 2 pi, then this would be pi over t. That's 2 pi t tilde, where t tilde is 1 over 2t. So the annulus partition function can also be interpreted in terms of a closed string that propagates for this proper time. And because of that interpretation, we need to know something about the closed string spectrum of the orbifold. And the main fact is that it's tachyonic, as I remarked about 20 minutes ago. And by standard methods, you compute that in the kth twisted sector, the ground state energy is this. And so the most tachyonic mode is, that's only, okay, yeah. That's if k is no bigger than this in absolute value. So the most tachyonic mode has an energy which is almost the same as minus 1/2, which would be the Navier-Schwarz tachyon if there was no GSO projection. So for integer n, our orbifold is almost as tachyonic as the Navier-Schwarz model without the GSO projection. Okay, now we can put the pieces together. This was our basic formula for the partition function, but with what I told you about J, we can write it like this. S is the set of all poles for G, but I'll write S1 and S2 for the poles where the real part of Z is 1/2 or 0. And for analytic continuation, we use one or the other of these functions. So a good formula for analytic continuation is this one, where I use the right k function in each case, depending on whether the real part of Z at a given pole is 0 or 1/2. And now everything is completely explicit. The functions k1 and k2 are some trigonometric functions that we discussed before. And we also have an explicit formula for G, and we can work out nice formulas for its residues. I won't write down the formulas because they're hard to follow in real time. I'll just discuss what it is we want to learn. We want to put z n of t into this integral that computes the annulus partition function to the logarithm of trace rho to the 1 over n. For t going to infinity, we're in the infrared region, where open string theory can be matched with field theory of the corresponding massless open string states. So there's not going to be a surprise there. T going to 0 would be the ultraviolet region in field theory. But of course, in string theory, there isn't an ultraviolet region. Rather, in string theory, we expect to see closed string exchange in the cross channel. If the closed string sector is tachyonic, which is the case if n is a positive integer, the integral is badly divergent for t going to 0. By standard arguments, if t tilde is the proper time in the closed string channel, then a closed string state where L0 and L0 bar are equal to h should make this kind of contribution to the open string partition function times a phase space factor that depends on p. So in particular, if n is an integer, a tachyon with h equals minus k over n will give this behavior. And concretely, in the formula I wrote for the Orbifold partition function, such terms come from poles of k2. Sorry, not poles of k2, poles that real part of z equals a half. So poles where k2 enters. So the k2 contribution is a sum of residues at these values of z. When the open string proper time goes to 0, which is the region where we expect a closed string interpretation, the residues are closely spaced, and the sum can be approximated by an integral. And after contour deformation, you get the expected behavior, where h depends on the position of the pole, which in turn depends on n. So from our formula, we recover the known tachyonic behavior when n is a positive integer. Well, okay, sorry. Because contour deformation is one of the step, it ultimately is poles of k2 that contribute the tachyonic behavior. So it turns out that tachyons come from poles of k2 of z and n in the strip where z is between 0 and 1. If n is a positive odd integer, the poles are at the right position to reproduce the known tachyons of the orbifold. But if we continue to the real part of curly n bigger than 1, the function k2 has no poles in the strip, and the closed string spectrum appears to be non-tachyonic. But we're not in the clear, because it turns out that as soon as n is not a positive odd integer, the functions that come in have double poles as well as simple poles. And the contribution of a double pole is not this expected behavior of a closed string state. There's an extra factor of t tilde, and we get instead this behavior. It's not possible to get that behavior in a unitary conformal field theory, but you can get that behavior in a non-unitary logarithmic conformal field theory in which L0 is not diagonalizable. A pair of states where L0 looks like this, where I2 is the identity matrix, can lead to the observed behavior because of this little fact I wrote here, that the exponential of minus a constant times L0 has a matrix element with an extra factor of t tilde. So a tentative interpretation is that as soon as n is not an integer, the theory becomes a logarithmic conformal field theory. Then if we continue further to the real part of curly n bigger than 1, it becomes non-tachyonic. The logarithmic behavior causes the range of p for which the entanglement entropy converges to be less than I would have expected. This result seems strange, and to explore it further, Atish Dalbekar and I have looked at another example, which I mentioned in responding to Hirose before. So for the simple dp brane crossing the Rindler horizon, the disk contribution to the Bekenstein-Hawking entropy actually has an infrared divergence independent of p. We wanted to see what happens in an example without this lower order divergence. And the example we looked at was type 1 superstring theory in R10 with the Zn orbifold that's chosen, as I said in answering Hirose, to avoid tadpoles. So again, there's no closed string tachyon when the real part of curly n is bigger than 1. There also were no double poles, so there were at least no double poles for massless states. Sorry. But there seems to be a massless scalar in the closed string sector that appears as soon as n is not an integer. I really don't know the proper interpretation of this. So in general, I don't know the proper interpretation of any of the results I've told you. Thank you.